Hello guys, we are going to be looking at plane transformations, and there is an exercise here under a specific type of isometry called orthogonal symmetries. Alright, so the exercise reads: find the analytic expression of the orthogonal symmetry whose axis is a line x minus y minus 1 equal to 0. Okay, so an orthogonal symmetry is basically an isometry, preserve distances. And what happens is that, let me just give you guys the little basic definition of what an orthogonal symmetry is. So I'm just going to call it S because we also call it a semitone. Okay, so if S, now its characteristic element is the axis, so we call it maybe S delta, something like this. So when we do this, it means that it is an orthogonal symmetry whose axis is delta. So if this is an orthogonal symmetry, such that the image of a certain point, let me say that point is A for example, such that the image under this transformation of a certain point A is equal to A prime. Okay, if the image of the point A under this transformation is equal to A prime, then two things happen. The first thing is that if the point A belongs to the axis delta, the axis is a line. So if A belongs to delta, then we can conclude that A and A prime are the same. And if A and A prime are the same, we are saying that A is what we call the invariant point. So A is the invariant point. Now the second thing is that if our point A does not belong to the axis delta, if the point A does not belong to the axis delta, then what happens is that the segment AA prime is a perpendicular bisector of the axis delta. So what do we mean by saying that the segment is a perpendicular bisector of the axis? It means that the line that is joining the point and the image is perpendicular to the line of the axis, because the axis is a line. Okay, so the line that is joining the point and the image is perpendicular to the axis, and the midpoint of this segment belongs to the axis. So it is going to be perpendicular to this axis, that is meeting the axis at 90 degrees, and also dividing the axis into two equal parts. Though we know we cannot divide, anyway we can divide the line, yes, but anyways, for sure the midpoint of this segment belongs to this axis. So that is basically what an orthogonal symmetry is. Now if the axis is a line, yes, you are going to call it an orthogonal symmetry. But if the axis is now a plane, we call that transformation a reflection. Alright, that is, if the axis is a plane, we call that transformation a reflection. Think about you standing in front of a mirror, that is the axis. You stand in front of a mirror and you realize that all points on your body are being mapped onto some other points that you'll see your image kind of inside the mirror, and the distance between any point and the image of that point on your body is from the mirror is equal. And if you draw a line that is joining the points on your body to the image of that point via the mirror, that line is going to be purely horizontal, provided the mirror was vertical. I'm just trying to give a practical example. Okay, now let us go back to the equation. So in this equation, we need to find the analytic expression. Now this analytic expression is also what we call the Cartesian equation. So I would like us to find the analytic expression, then we move backwards from the analytic expression to the complex representation of this similarity transformation, that is this orthogonal symmetry. Okay, then I think I'll now show you how to go back forward. But anyways, it's very important that we use these two properties. Anyways, you are just going to focus on this particular property, putting in mind that the point does not belong to the axis. Alright, so here the only information we have is the axis, which is x, which is the line x minus y minus 1 equal to 0. That's the only information we have. But anyway, since we know that this is an orthogonal symmetry, then we have to use the fact that we have to use this number 2. We have to use the fact that the line segment AA prime is a perpendicular bisector of the axis. In other words, we can split this second condition into, or this second case, into two different cases. The first case will be that the vector AA prime is perpendicular to this line, alright, or anyways the line, we can say the line AA prime is perpendicular to the axis, or we say the vector AA prime is perpendicular to the direction vector of this line. Then the second condition is going to be that the midpoint of AA prime is definitely belonging to this line. So let's use those two conditions because we have the line. Alright, so my axis, let me just say let A be the point. Let me just say A is x comma y, okay, and A prime is x prime y prime. Now the analytic expression such that this happens. Alright, so I'm just going to call that orthogonal symmetry S with axis delta. So where this line is delta. So the analytic expression of this orthogonal symmetry is basically a system that relates the images of every point with the point themselves. So it's going to relate the x and y coordinate of the image of this point to the x and y coordinate of the point itself. Then we now see how we can take it to the complex plane. Okay, now like we said, if we don't want, we can use the fact that okay, the line that is joining AA prime, that is joining A to A prime, is perpendicular to the axis. In other words, the gradient of the line AA prime times the gradient of the axis is -1. Or we try to find the vector AA prime, which is just A prime minus A, and then we subtract, we take the vector AA prime, then we multiply that vector AA prime with the vector with the direction vector of this line, and we equate to 0. That is, we do the dot product, right? Because that's a condition for two things to be perpendicular. You guys should give me a minute. This computer is running low, so let me try to charge it, then we proceed. Okay, so I prefer to go with the fact that the gradients, the product of the gradients is -1. Okay, so the gradient, let us find the gradient of the line AA prime is equal to, we know it is changing in y over change in x, so it is y prime minus y divided by x prime minus x. Now the gradient of the axis is equal to Now if I want to write this axis in the form y equal to mx plus c, we are just going to have y to be equal to x minus 1, and the gradient is a coefficient of x, which is 1, so the gradient is 1. So first things first, we have that the product of the two gradients is equal to -1. Okay, so this man times 1 times 1 is equal to -1, which just means that the both numerators are, one of them is negative of the other, so y prime minus y is equal to x prime, is equal to x prime minus x. I can call this man equation 1. Okay, now the next thing to do is that the second condition is that the midpoint, right, the midpoint of the line segment AA prime, let us find the midpoint. The midpoint, yes, the midpoint of the segment AA prime, what is it equal to? We have to we sum the x coordinates and we divide by 2, so x plus x prime divided by 2, and then the y coordinate is y plus y prime divided by 2. Okay, that is what we have. Now this midpoint is supposed to belong to the axis because the segment AA prime is a perpendicular bisector. Okay, so we are already done with the word perpendicular in the first case. Now let us concentrate on the word bisector. Okay, so if we have that, this midpoint should belong to the axis. Now if the midpoint belongs to the axis, it means that the x coordinate of the midpoint minus the y coordinate minus 1 is equal to 0. So the x coordinate is just x plus x prime divided by 2. So I have x plus x prime divided by 2 minus the y coordinate. Oh, they have taken lights. Anyways, let me just be fast. Now the y coordinate is y plus y prime over 2. That's the y coordinate. So we have y plus y prime over 2. Then we have to subtract 1, then we equate everything to 0. Okay, so if I multiply all through by 2, I'm going to have x plus x prime minus into y plus y prime minus 2 equal to 0. Now I will try to write so this just means that we have x plus x prime minus y prime equal to 2. Alright, this is the second equation. Here's our second equation, equation 2. Alright, so we are just how we are going to combine these two equations together. While combining these two equations together, we now see how we can relate x prime and y prime. Okay, so from the two equations, I will try to find x prime in terms of x and y, and I'm also going to find y prime in terms of x and y. So let me write the two equations as a system. So the first equation, I'm going to rearrange it. I can put x prime minus y prime, that is, I'm subtracting y prime on both sides. So I'll carry y prime to the right hand side, is going to meet x prime. Then I will add x on both sides. When I add x to negative y, I'm going to have x minus y equal to x minus y. Now in the second equation, I'll also write x prime and y prime on one side. So the second equation, what I see here is x prime minus y prime equal to, now x prime minus y prime equal to we are here, x prime minus y prime equal to 2 minus x plus y. So I'm going to put minus x plus y plus 2. That is what I have. Alright, now from here, what am I going to do? I'm going to write x prime in terms of x and y, and I also write y prime still in terms of x and y. That's what I'm going to do. Okay, there's a little error up here, right? I was really wondering why we have this. So the little error is with the fact that we forgot a negative sign to multiply with x prime minus x. So here is instead going to be negative x prime, right? Negative x prime plus x. Okay, now here instead of having x prime plus y prime, instead of having x prime minus y prime, I will just carry the negative x prime to the left hand side. It's going to be positive, and this sign here is going to be positive. Oh, so this sign here is going to be positive, and then now for the x and the y, we are going to have x plus y instead. Here is going to be x plus y. Voila, that's what we have. Now I think it's now very easy for us to find x prime and y prime in terms of x and y. If we add the two equations, so I'm still going to write my system. Okay, if we add the two equations, we realize that y prime is going to disappear, and we are going to have 2x prime is equal to x will cancel with x. Okay, x will cancel with x, and we are going to have here 2y plus 2. If we divide all through by 2, we are going to have x prime to be equal to y plus 1. Now if we subtract the two equations, x prime is going to cancel. Then we are going to have 2y prime is equal to, now x minus negative x is 2x, and then 0 minus 2 is negative 2. Y is going to cancel. So if you divide all through by 2, your y prime will be equal to x minus 1. Okay, so this is the analytic expression of the orthogonal symmetry. Now if we want to get the axis, that is, if we want to, maybe if you're giving the analytic expression like this and they ask you to get the axis, we are going to just, all we need to do is to get the axis, to get the axis, we try to to get the axis. It's actually the invariant axis, okay, because the image of the axis is itself. So to get the axis, I'm going to replace x prime here with x, and I'm going to replace y prime here with y. Alright, so let us try to see. So if we are replacing x prime with x and y prime with y, then definitely this is what we are going to have. I'm going to have here x, and I'm going to have here, I'm going to have here x, and I'm going to have here y. Now I can just carry the x in, wait. I can just carry the x in the first equation and replace it in the second equation. Anyways, if I carry the x in the first equation and replace in the second equation, then it's going to hold true. Yes, it's going to hold true. So from here, what do I do to actually have my axis? Anyways, from the first equation, you realize that your y will be equal to x minus 1. Alright, so the two equations are the same. You see now? So first equation is the same as y equal to x minus 1. Second equation is the same as y equal to x minus 1. So y equal to x minus 1, it therefore means that x minus y minus 1 is equal to 0. Anyways, you just conclude from here. X minus y minus 1 is equal to 0, which is our axis. Now let us focus on maybe getting the complex representation of this orthogonal symmetry. So we this is the analytic expression. Okay, now if you want to get a complex representation, all right, what we are going to do is we are going to start by multiplying y prime with an I, because in the complex representation we have z prime is equal to a complex number a times the conjugate of z then plus a complex number b. So this z prime here is x prime plus iy prime, the affix of the image. This z bar here is a conjugate of the affix of the point, which is going to be x minus iy, since our point a is x plus is xy, so the affix z is going to be x plus iy, therefore the conjugate will be x minus iy. Alright, so to have x prime plus iy prime, I will start by multiplying. I'll start by multiplying my my y prime here with an I. So if I multiply with an I, we have I here, and then we have this. Alright, then we add the two equations. When we add the two equations, we have x prime plus iy prime. This I is a complex number, not a vector. So x prime plus iy prime will be equal to y plus ix then plus 1 minus I. Okay, so I'm just going to keep this 1 minus I, then I'm going to focus on y plus ix. Okay, so I'm going to show you two methods. Alright, I'm going to show you two methods which you can use here. So since we know that since an orthogonal symmetry, then we have z prime to be equal to a z bar, like I said, a z bar plus b, where a and b are complex numbers. This z bar here is x minus iy. Alright, but here the I is instead with x, so we need an I to be with y. So I'm just going to write it as x prime plus iy prime to be equal to, I'm going to factorize an I. Alright, I'll factorize the I. If I factorize I from y, I need to actually have a certain number, but I'm going to have 1 over I, so that when I multiply the I with 1 over I, I'm going to have 1. When I factorize I from x, I'm going to have x. But 1 over I is the same as negative I, because if you multiply the numerator by negative I, you multiply the denominator by negative I. That's a conjugate. I times negative I is negative I squared, but since I squared is negative 1, negative I squared is going to be 1. So everything here is going to boil down to negative I. Alright, so let's just write the x first. So we are going to have x minus iy. So we are going to have here x minus iy. Then now we are going to be left with x minus I. Alright, we are going to be left with x minus I. So clearly we can see that our z prime will be equal to I times z bar plus 1 minus I. So the complex number a is I, and the complex number b is 1 plus I. So to always know if this is an orthogonal symmetry, then we always need the fact that the modulus of the complex number a should always be equal to 1. In this case, it is I and the modulus is 1, so it is definitely an orthogonal symmetry. Okay, and if it's an orthogonal symmetry, then there is a condition that the complex number a times the conjugate of the complex number b then plus the complex number b is always equal to 0. A very good condition that we have to note. Anyways, like I said, I'm going to show you guys two methods, because maybe this might always be tedious for you to identify. But the basic way of always doing it is using the fact that if z is equal to x plus iy, if z is equal to x plus iy, it therefore means that the conjugate of z is going to be x minus iy. Alright, now we are going to find x and y using these two complex numbers. So if we add the two equations, z plus z bar will be equal to 2x, which means that x is just equal to z plus z bar all divided by 2. Now if we instead subtract the two complex numbers, we have z minus z bar, to be equal to the x is going to cancel. We are going to have 2iy. Alright, which means that this is supposed to be z bar, sorry. just that the keyboard I'm using is very small. So we are going to have z minus z bar to be equal to this. So your y is going to be z minus z bar divided by 2i. Okay, so that is y. So your y is equal to z minus z bar divided by 2i, and then your x is that. Okay, now all we need to do is we replace this and this back into this step, and we simplify. So let's try that and see what we have. So this man is already z prime. Alright, so we just have z prime is equal to, now in the place of y, like I said, I'm going to replace it with z minus z bar over 2i. Then anyways, then in the place of, where is it, we have I times x. In the place of x, we replace it with this. Alright, then we multiply with I, so it is plus I times x, then plus 1 minus I. You just keep the 1 minus I constant. So your z prime will be equal to, now we can find a way to remove the negative sign from the denominator by multiplying the numerator by I, multiply this one also with I. Alright, and then you also multiply the same denominator with I. I times I is going to give us I squared, and I squared is negative 1. So we have the negative sign here, but this negative sign can come to the numerator and convert this man to positive and this man to negative. Okay, now the next thing to do is that we realize that the first two terms have the same denominator, so we just have to add their numerators. So you are going to take this numerator plus this other numerator, but this other numerator will also will carry I, since that's a factor. We have I here and we have I as well. Okay, now we see that negative iz or negative zi plus zi is 0. Let me add this other man first. So plus this, as I know you guys have already seen the answer, because this man and this man are going to cancel to give us 0. Now next thing is that when you add the numerator, it will be 2 times itself, and the 2 is going to cancel with the denominator. So definitely we are going to come back to z prime is equal to iz bar plus 1 minus I. Alright, so I think we have come to the end of the video. If you love the video, you like the video. If your resolution, I was supposed to say this at the beginning, but if your resolution was not the best, try to increase. If the video was blurred in your device, try to increase the resolution part so that you see the video clearly. Okay, see you guys in the next video.